So on your AP Physics 1 formula sheet, this is what the friction equation looks like. If you haven't looked at it yet, this is what it looks like. Nope, actually it's... This is what it looks like on your formula sheet. Where these vertical bars are what?
Absolute value.
Absolute value. In physics, absolute value tends to mean magnitude. Okay, so this just means it doesn't matter the direction. The magnitude of the friction force is less than or equal to the coefficient of friction times the magnitude of the normal force. The absolute value bars are literally there to say don't worry about whether these are positive or negative. Okay, just consider their magnitudes. Okay. Now, flipping physics yesterday told you that this actually encompasses 3 equations for this unit. Hello.
I'm worried Kyle's not here.
Remind me at the end of the period to mark you unabsent.
I'm worried Kyle's not here.
So there's 3 equations built into this single equation. One is the kinetic friction equation, which is probably the easiest to understand. So the kinetic friction force, I'll use a subscript K, is exactly equal to the coefficient of kinetic friction times the normal force. Okay. That's in my opinion, the easiest one to understand because there's no inequality. Right? The friction force, the kinetic friction force, is the same regardless of whether the object is moving 1 meter per second or 100 meters per second. It's the same. Okay. The static friction force is a little more complicated, and that's where the inequality symbol comes in. So the static friction force technically is less than or equal to the static coefficient of friction times the normal force. And remember that the static coefficient of friction is always larger than the kinetic coefficient of friction, which is why it's harder to get something moving than it is to keep it moving once it is moving. And that has to do with all the peaks and valleys of everything.
Let's go a couple of quick announcements. Welcome to Friday. It's great to have a Friday. Just a reminder tonight, we are the visiting team at the FAC against the green team. Even though we're the visitors, remember, it's still our house. Also, a reminder for Thanksgiving providers, all you 5th period classes, your Royal Times. Teachers go over with your students about Thanksgiving providers and what to bring. I've seen a steady stream of students going into the library, dropping off food items. It's been a long-standing tradition at Richmond High School for Thanksgiving providers. So do all you can, do what you can, and bring your food items up through next Wednesday to drop it off in the library. Again, it's a great day to have a Friday, so go Royals.
I think this is a terrible day to have a
Great
Friday.
day to have a Friday.
No, this is a bad day to have a Friday.
I mean, isn't a Friday?
Saturday would be a good day to have a Friday.
Yeah.
Okay. Okay, if you forget about what the announcements were, they'll be on the video, so you can hear those again. So the static friction force is the one that's less than or equal to the coefficient of friction times the normal force. What does that mean? Well, that means if I have an object, and for those in the back that can't see, I just got a wood block with some masses on it, and I push on it. Well, first of all, when I don't do anything, there's no friction force, right? If there was a friction force, it would be accelerating in the direction of the friction force. Obviously, it's not. So there's no friction force here. If I push on it a little bit, just a little bit, it's not accelerating. It's not even moving. So that means there must be a little friction force opposing it. Now I'm pushing harder, but it's still not moving, which means the static friction force must have gotten larger.
I overrid the attendance bell. So do your attendance.
So if I push harder, the static friction force has to get bigger in order to still maintain a net force of 0. Okay? Until it gets to the maximum. There's a maximum amount of static friction force that can be exerted by the table on the block. And if I overcome that with my applied force, that's when it starts to move. Okay, that's when I've overcome the maximum static friction force. The block starts to move. And then the static friction turns to kinetic friction. And so the friction force actually goes down because the coefficient of kinetic friction is smaller than the coefficient of static friction. Now, this one here, you need to understand conceptually, but it's very rarely actually used. You actually very rarely use the inequality. It's there to just show that the static friction force can vary, but we're usually more interested in the maximum static friction force. Usually that's much more interesting, much more useful than just the static friction force in general. And that's when it's exactly equal to the static friction force times the normal force. Okay. In our next unit, we'll solve this problem. You're driving in your car at a certain speed, and you take a curve, a circular curve at a certain speed, and the question will say, based on the coefficient of friction between the tires and the road, what's the maximum speed you can take that turn in before you start sliding? Okay. That's when you've reached the maximum static friction force able to act on the tires. If you exceed that, if the opposing forces exceed that, then the car starts to slide. So that's very important to know. So this, again, much more useful than that in practical everyday situations. So when you're doing friction problems, these are the equations that you end up using. Okay? But you want to conceptually understand the way that static friction forces can, in fact, vary. Sound good? Yeah. Now, one thing I want to note, let's say we have a block and I'm pushing on it and it is moving. So we're dealing with kinetic friction. I got the weight force mg. I got the normal force. I apply a force to the right, so I call that force applied. And I have a kinetic friction force to the left. Note the equation relating the kinetic friction force and the normal force. Force of kinetic friction equals coefficient of kinetic friction times the normal force. Up until now, say with projectiles, you have a projectile motion problem and you're asked to find something. And so you pick a direction, the x or the y direction, and you solve it. You try to solve that problem using your chosen direction. But if you end up with an equation, a single equation with two variables, two unknowns, then that tells you got to go to the other direction. Generate another equation, and then you can find your result, your answer. With forces, same thing. You want to analyze the forces on a ramp, on a block sliding down a ramp, a frictionless ramp, we'll say, and it asks for something, the acceleration or something. It asks for anything, and you generate an equation by looking at one of the directions of motion, but you realize at the end of that, oh, I have an equation with two unknowns. That tells me I got to go the other direction. It's a central theme in physics. When we're dealing with friction, you will always need to do both the x direction and, not or, and the y direction. And that is because the friction force will be in one direction, the normal force will always be perpendicular to the friction force. Okay? So you're always going to, in a tough friction problem, you're always going to be dealing with both the x and the y direction, so just be ready for that. All right? All right, now briefly, what's the recording? Yes, briefly, maybe not so briefly, I want to show you, because Mr. P talked about how coefficients of friction are not determined using theoretical physics. You really can't do that. Theoretically, you could, but you would need more information than you could practically get. So what we do to measure, what we do to determine coefficients of friction between, say, that block of wood and the table surface, or between, say, rubber tires and asphalt, which again is very important if you're an engineer and you're designing roadways and off-ramps and stuff like that. What you need to do is actually experimentally determine those coefficients of friction. They're necessary. You need to know what they are. Accident investigators that go out to analyze accidents measure skid marks, and based on the work done by an engineer that's knowledgeable in physics, they look up in their book and oh, this car had this much mass, it must have been going this fast when it started skidding out and caused the accident. So it's important stuff to know. The coefficients of friction are important to know. So how can we experimentally determine it? Normally, this would be sometimes when we have time. It's very hard to find time in AP Physics 1 because we have so much stuff to learn, and it's pretty rigorous. But sometimes when we have time, we do this as a lab. So I'm going to show you how I can pretty easily determine the coefficient of friction between the block, the bottom surface of the block, and the table here. Okay. Essential theme in science, you do as many trials as you can. The more trials you do, the more better your data is going to be, right? It's grammatically correct, right? What I just said? Yes. And so I'm going to show you, and in the process of showing you, I'm going to actually give you some insight into how to use spreadsheet software to keep track of your data. Many of you probably already know how to use Excel pretty well, or Google Sheets, although I would recommend getting familiar with Excel. Google Sheets is actually better now than it used to be. But in the future, you guys, a lot of engineers in here, in the future you're going to be using much more sophisticated software like MATLAB or other software. And so you want to understand how spreadsheet software works and how it makes your life a lot easier when you're doing certain types of laboratory investigations. So I'm going to do a quick experiment that without the software would take much longer. But I'm going to take 4 data points, put them on a graph, and determine that coefficient of friction really quickly. So I'm going to be using, first let's explain the experiment. Got a block of wood with a string on it. I'm going to hook my force probe up to the string. Can I get another? And then I'm going to pull it along the surface of the table at constant speed. I'm going to do my best to do constant speed. If I'm pulling this block at constant speed, the tension force that's pulling it should be exactly equal to the friction force, right? And the tension force that pulls the block this way is the same as the tension force that pulls in the opposite direction on the force probe. So I'm directly measuring the tension in the rope, in the string, but I'm indirectly measuring the friction force, right? When I start pulling on it here, you see the force down there. I start pulling on it and the force goes up, right? And I'm actually going to graph that, as you'll see in a second. And then I'm going to change the block's mass by adding masses on top of it, okay? And then I'm going to repeat that, and then I'm going to add more mass, and then I'm going to repeat that, and I'm going to be collecting data. Well, what data do I need? Well, I'm using the kinetic. It's going to be moving, so I'm going to be dealing with the kinetic friction force, which is exactly equal to the coefficient of kinetic friction, which I want to determine experimentally, times the normal force. So I can put these on a graph, right? I can graph the kinetic friction force versus the normal force. And if I did that, how would I determine and with different values, right? I changed the normal force by changing the mass of the block, and then will give me a new friction force. How can I use that graph, do you think, to determine the coefficient of friction? Starts with an S. SL. What if I make a graph of Y versus X?
Slope.
And I want to determine what this is.
You get the slope.
You get the slope.
You have the coefficient.
Yeah. If this is on my Y-axis, this is on my X-axis, and it's linear, if it's linear, then our coefficient of friction should be the slope, right? And if the coefficient of friction doesn't change, the graph should be linear. Because if it was a curved graph, that would imply that the coefficient of friction actually changes depending on the mass or weight of the object, or normal force on the object. Okay.
Which happens when you lose the weight or the shape of the object.
We're gonna change the weight and see what happens. Okay, we're gonna take several data points. So I've described how we're gonna set up the experiment. Let me show you how I'm gonna analyze the data. First, I made a couple columns: mass, weight, and then normal force and friction force. These are the variables that I want to graph: normal force and friction force, right? Normal force, friction force. Whenever you use Excel or Google Sheets or any other software spreadsheet program, the first column is the x-axis, the second column is the y-axis. We want the normal force to be the x-axis, the friction force to be the y-axis. Okay. So I'm going to first, I already measured the mass of the block. It's 266 grams. So I'm going to put that in mass, 0.266. Not 266. We got to put in 0.266. We got to convert that to kilograms right off the bat. And then because I don't want to have to do a bunch of math on my calculator all the time, I'm going to let Excel do the math. So I'm going to say the weight, I hit the equal sign, right? That tells Excel I'm about to do a calculation, about to put in a formula. That's going to equal, and then I click on this cell, and then I multiply that cell by 9.8, and I hit enter. And it does it by itself. What's nice about that, I'm going to do 4 data points, is if I grab the little box in the bottom right, and I drag it down, and it applies that same formula to every subsequent cell, using the cell that's to its left. It doesn't use that original one, it follows you down. Okay. So if I had 1 kilogram, I'd expect the weight to be 9.8 newtons. If I put 1 in there, it automatically goes to 9.8. So it's a nice way to avoid just having to do a bunch of tedious calculation over and over again. No, if you do stuff like this, it'll most likely be built into the Pivot Interactives lab, unless we go out and we stop this stuff and we can actually start doing labs again, which I'm not, at this point, I'm not foreseeing this year. Yeah, who knows? I hope not. I hope not. I know some people want Thanksgiving to bleed in the crowd. I want to keep, I don't know. Anyway, so the normal force, notice that the normal force, I'm not going to draw the free body diagram to show you that the normal force is the same thing as the weight force. You should be able to know that, right? The magnitude of the normal force on that guy is equal to the weight force because it's not accelerating vertically and there's no ramp here. So I'm just going to say the normal force equals that guy. And hit enter, and it makes it there. And then if I drag that down, it does the same thing. And if I put a number here, then it's going to show up there. Okay? And then that means I need to measure the friction force. Well, that's my experiment. That's what I need to do. I need to conduct the experiment now. So I'm going to, and I'm going to do my best. Again, I need to do my best to pull it at constant velocity, because if I pull harder, then it will accelerate. And I won't be measuring the friction force directly. So I'm going to be careful to try to pull it along the tabletop at constant velocity. I think I'm doing all right. Yeah. It gets harder with the more weight on it. Okay, and then so these are all just force data points, right? I'm plotting force versus time. So each one of these little things is a force at a specific time. A lot of data points. And I can just do a quick statistical analysis. I think I messed up right about here. So I just do statistics, and this thing comes up. Statistical analysis for us here just means get the for this particular what I'm doing now. It just means get an average value. So a mean value. So my mean is 0.7483 newtons. Okay, so I just put that here. 0.7438 newtons. So there's my data point, right? My ordered pair: normal force, friction force. Now I'm going to do it again. I'm going to do the trial again, but I'm going to change the normal force. I'm going to add 1 kilogram of mass onto the block. So if I add 1 kilogram of mass to 0.266 kilograms, I get 1.266. And when I hit enter, these adjust accordingly, so I don't have to do anything else. I don't have to do any calculator work. Excel does it for me. And then I just measure the next trial. I just do it again. So pull it, hopefully at constant speed. Ooh, got some bumps here. Oh, that's not too bad. I think it's the best over here. All right, and so I got an average force there of 3.664 newtons. So I go 3.664. All right, well now I'm going to do the same thing, but I'm going to put another kilogram. I put another kilogram, so now it's going to be 2.266 kilograms. Hit enter. The other ones automatically go. So it's a very efficient way, right? Efficiency is key in school, in laboratory experiments, in your job. Whenever you get your job, the more efficient you are, the more you'll be recognized as being efficient by your boss, and they'll appreciate that because the more efficient you are, the more money you're making your company. Yeah. More efficient, more money, right? All right, so I got to measure the friction force now. But then more money, more problems, right? True. Well, yeah. Otherwise, there's no point in them having you as an employee. All right. Notice we get that characteristic bump here, right? That was the maximum static friction force before it actually started moving, right? You saw that in Flipping Physics' video from yesterday, right? I pulled it from rest, and so the static friction force was less than the maximum until it reached that maximum value, and then it drops back down because that's when it becomes kinetic friction. All right, so I think that worked out pretty well. Nope. Move over to here. About there. So now my mean force 6.217. So I put that here, 6.217. All right, and do one more trial. I'll add 1 more kilogram. So 1 more kilogram brings that to 3.266. Again, everything else gets populated automatically. And so all I need to do is run my last trial. Oh, that's not very good. I think it was better towards the end there. Right about there is probably pretty good. So I get 7.919. So 7.919. And I'm going to throw this data point in there too. Because right now there's 0 friction force. And zero sorry. Never mind. Sorry. Don't listen to me. I don't know what I'm talking about. Now what's nice about Excel, I can put this on a graph. So I highlight the cells, and remember the first column is always the x-axis, second column is always the y-axis. So I just put those I highlight those cells, go to insert. All kinds of charts you can make with your data here. Generally, we pick the scatter plot, where it just puts data points on the graph. It looks pretty linear. I did think I did do the last one pretty terribly. So I'll blame Kurt for that. So I have my data points plotted here, and now if you're going to put this in like a report or something, you can label the axes, you can label the thing itself, you can do all kinds of formatting on it to make it look nice, and then you can click that button and add a trend line. So just fancy name for line of best fit. Last period it was better than this one. Sorry about that. And then I can get an equation for the trend line. You just right click on the trend line itself, format it, scroll down, display equation on chart. There's my equation. Okay. What's that? Yeah. But you can only throw data out if you know. Well, I guess I could have thrown it out. Yeah. I knew I didn't do very well, but I'm going to use it all. Okay. And then I get an equation. If you can't see it, it says y equals 0.2457x plus 0.3837. We're going to ignore the y-intercept. The y-intercept usually does mean something. It's tied into like error analysis and stuff like that we're not going to really get into. But my y in this case is the friction force. My x in this case was the normal force, which means that the slope in this case should represent the coefficient of friction. So I have just determined the coefficient of kinetic friction between that block and the table as 0.2457 or about 0.25. Last period we got 0.24. So there's experimental error here, and I wasn't as careful as I probably should have been. What are the units? There are none. It's one of the few unitless numbers that we'll find this year in physics.
It's united in the coefficient of friction.
Well, it's newtons per newton.
That's the
Yeah. Because look, if we take the equation, the friction equation, and solve it for coefficient of friction, it's literally the ratio of the kinetic friction force to the normal force. Right? That's one way of thinking about the coefficient of friction. It's the ratio of the friction force acting on the object to its normal force. This is measured in newtons, that's measured in newtons, so the units are newton per newton, or just no units. Right? So this is one of the few numbers that when you solve for it, nothing gets tacked on the end. Okay?
That means that you always have to put it alongside the coefficient of friction to the number, right?
Wait, say again?
Don't you always, whenever you're listing the coefficient of friction, do you need to list it as the coefficient of friction so that everyone else knows what it is?
Well, you give it the symbol, mu. Specifically mu sub k or mu sub s. Yeah. If you're dealing with friction forces, people know what this is. People know what mu is. And people write mu differently, by the way. Some people write it like with a really long, maybe not that long, but like that. I just got in the habit of doing it like that. Yeah. Okay. Now, before we watch the videos, I want to point some things out. Mr. Flipping Physics, he does do things a little bit differently. So when we have this equation, x equals x naught plus vx naught t plus 1/2 the acceleration in the x direction times the time squared. I've gone over this plenty of times before, but I just want to remind you because we are going to be doing kinematics in this unit. Mr. P likes subtracting x naught, and he doesn't do this. He just, assumes it's done like this. Final minus initial position is change in position or displacement. These go away. And then Mr. P likes saying v naught times change in time, but change in time just means time interval, right? We assume, because we have these naught subscripts, that t naught is just 0. We start our stopwatches at the start of the motion. And then, so then you'd have plus 1/2 the acceleration times change in time squared. So he does use this equation, and even in the video today, because we are dealing with ramps, the videos that we watched today, we're dealing with ramps, he kind of gets away from delta x's and calls them delta d's. Either delta d parallel to the ramp, which means displacement down the ramp or up the ramp, or displacement perpendicular to the ramp. I never use delta d's in AP Physics. That's what we use in on-level and pre-AP Physics. Delta d's, just I'm not going to use it, but just understand that's what Mr. P's using when he does it. Some other things when he does his free body diagrams for objects on inclines. And it's good to know this and be able to adjust. If you can adjust your process based on different notation, different ways of notating the same thing, and you don't have trouble with it, that means you really know the concepts, right? So I think it's good. So if I have this free body diagram, Mr. P likes calling the weight forces Fg, normal force, and let's say the object is not sliding, so we have a static friction force. Here. Now Mr. P likes doing the vector decomposition and then redrawing the free body diagram like this. So we would decompose Fg, and then because this is the component of Fg that is perpendicular to the ramp, he puts Fg perpendicular, and then Fg parallel. And then he actually redraws the free body diagram. And then he'll redraw the free body diagram with both of these vectors originating at the dot. And so you might like to do this. You might like to do it that way, and I'm fine with you doing it this way. And then he would say, all right, Fg parallel goes here, or perpendicular, sorry, Fg perpendicular. And then Fg parallel, you can put it here. But I've been telling you for years now that you can move vectors around and they deal with them the same way, right? They're just tools that we use to analyze situations, and in vector analysis, you're allowed to move them around on the computer screen, on the page, whatever, on the board. And so Mr. P likes doing it this way. I tend to, and you can do it however you want, but this is the way that I've always done it. I label my weight forces as mg. And then instead of saying off to the side, well, Fg parallel is Fg times the cosine of the angle, I just put it on the free body diagram. And you've seen me do that a lot. Mg cosine theta, Mg sine theta. I'm not trying to skip steps here. I'm just saying that it just makes it easier for me to throw that into my equations when I'm using Newton's laws. So, yes, it looks a little different when Mr. P does it, but I feel like Mr. P, and because I have online students that need to see this, I feel like it's an excellent, still recording. I feel like pick whichever way you want. Pick whichever way you want. If you like the way Mr. P does it, do it Mr. P's way. If you like this way, I'm not saying this is my way. This is the way that my community college physics professor taught me. So that's the way I've always done it. Okay. But understand that when you see him doing things slightly differently, when he uses the slightly different kinematic equations, they all mean the same thing. They are all the same equations. They're just written. They're notated somewhat differently. Okay? All right. That's it for the video.